Okay, you wanna go over these? Everybody done? No? Are we still working? Jared, still working?
Yeah.
Okay. You ready? You're ready. Okay, let me see, a charging capacitor. Jared, are you ready?
Yeah.
Okay. What'd you get for the first one? What is the capacitance of the capacitator?
I got 7,466. 10 to the 7.
Times 10 to the minus 7? Okay, that's 746.6 microfarads.
So 746.
0.6 microfarads, which is correct. You just had 10 to the minus 7. So you just start out with Q equals CV, or Q equals VC. You want to go with the shopping club formula, and just fill in the blanks. The second one, how much charge in coulombs is developed across the capacitor? Anybody want to venture a guess? I get 4.55, I could be wrong, 4.55 times 10 to the minus 4th coulombs, or 455 micro coulombs. Did anybody get something different? You got it?
You could put J right like for joules.
No, charge is coulombs.
Okay. So
The only time you use joules is in that energy formula, this guy here.
okay.
Convert the following to microfarads. Okay, so that first one I get, if you move the decimal places, you have to move it to the right 6 places, so that's 14 microfarads. The next one, I moved it 6 places to the right, and I got 5,600 microfarads. Okay? Then from pico to micro, you got to move the decimal to the left. I get 0.002547 microfarads. Wait a second, is that right? Yeah. Pico, yep. 1, 2, 3, 4, 5, 6. Okay, and then everybody get that? Is that the same? Okay. Then I got the next one, 2945 nanofarads. I got 2.945 microfarads. Next one, 0.596 microfarads. And now we're converting to picofarads, which is 10 to the minus 12th. So these are little guy capacitors. I get 285.9 picofarads. The next one, 385,000 picofarads. Next one, 230 picofarads. Micro pico. 1, 2, 3, 4, 5, 6, yeah. And then the next one is 6, from nano to pico, 6.8 picofarads. Okay? Number 5, it talks about, that's that formula W equals 1/2 CV squared. So you have a 65 microfarad capacitor, 90 volt source, plug in the values, and I get, and you have to square the voltage, I get 0.263 joules. How much energy is stored? The next one, same formula, but you're given the energy in joules and the voltage. You have to come up with the capacitance. And I get 4.97 millifarads. Got that? Capacitor plate has 10 square millimeters, plate separation of 0.1 millimeter. The dielectric material is air, that means the relative permittivity is 1. What's the capacitance? So I use this formula, C equals this guy here, area over diameter, or area over separation distance. And I get 0.885 picofarads. No? No, what'd you get? You want me to go over that one?
Yeah.
Okay. So the area is 10 millimeters. 10 millimeters squared. We've got air, so relative permittivity is 1, so epsilon is now simply the permittivity of free space, so it's 8.85 times 10 to the minus 12 farads per meter, okay? And the separation distance is 0.1 millimeters. So we're just looking at the dimensions. We can get rid of millimeters and get rid of that guy up there. We multiply that out and we get what? .85 times 10 to the minus 10. Farads, millimeters over meters. And 1 meter is equal to 1,000 millimeters. Just do a little bit of dimensional stuff here. Now we can cancel the meters, millimeters, we're only left with farads. But we have to divide by 1,000. And that leaves 8.85 times 10 to the minus 13th farads. So I have, what did I say? 88. So if you so if you move this decimal place there, you've got 0.885 times 10 to the minus 12 farads, or 0.885 picofarads. Is that right? Where did I lose you?
I'm still trying to figure it out. Where did the .1 go?
This is the separation distance between the plates, 0.1 millimeters.
Right.
has the guts to keep emailing me. Did you get it, Royce? Or are you still have a question?
I'm working
You're working on it? All right, well, let's do the next one, and maybe you'll have two questions. Okay, so the next one, 25 microfarad capacitor, you have a plate area of 15 square millimeters. Mica as the dielectric material, we're getting fancy. How far are the plates separated? And mica, so here's the formula. Since we're using mica, we have to find ER from our table. So relative permittivity is 5. I'm glad I'm doing this one because I used 1200. I misread that. So the relative permittivity is 5. Is that right? For mica? Okay, and so that's this guy here, 5, and epsilon 0 is this. And we have to find now the plate separation, so we have to find D. So rather than write that whole equation again, I'm just gonna cross multiply, put D up there, and put this here. See what I did? Okay. Now I gotta multiply that out since I used the wrong number. So we have 15. I get 2.655 times 10 to the minus 5th. And what is that? That's millimeters squared times farads divided by meters. So this is farads. So I have farads down below as well. Okay, so my farads cancel, and I have 1 meter is equal to 1,000 millimeters. So now I can cancel meters. I can cancel millimeters there and get rid of the exponent. That leaves millimeters remaining. So I have to divide this by 1,000. .655 times 10 to the minus 8. Millimeters. Man, those plates are close together. It's almost like the diameter of an atom. Okay, so I'm going to change those numbers around next time and make it more reasonable. But that's what I get. Did you get that? false? When the plate area of the capacitor increases, its capacitance increases. True. Is that right? Look at the formula. When that guy goes up, the plate area, capacitance goes up. True or false? Glass is a better dielectric than ceramic. That's false. Did you say false? Okay, it's true.
Is it true? Is it true?
No, it's false. You're right. You have to just look at the table and
That's right.
I never really said what exactly a dielectric is. I'll have to go over that. And then the last one, 11, capacitor has a fixed charge and is not connected to an outside circuit. Wow, okay. So you have two plates. There's a voltage here, there's a charge on the plates, fixed. And you pull those plates apart, what happens to the voltage between those two? You would think it'd go down, wouldn't you? I mean, intuitively, I think it would go down. Well, let's look at the formula. We have Q equals CV. All right, that's our starting point, and we have this guy formula here. That if we replace this for C, we have Q equals this. Okay? Now let's just solve for voltage. Let's solve for voltage. So voltage equals charge times the plate separation divided by area times permittivity. So as I increase distance, as that D goes up and increases, the voltage between the plates goes up. Remember, voltage is work per charge. It's joules per coulomb. So I'm physically pulling apart those plates. I'm adding energy to that system, physically pulling them apart. Voltage goes up. I don't kill myself in the meantime. So that not all this stuff is intuitive. Sometimes it's counterintuitive. Okay? Any questions? What time is it?
7:14.
7:15. Okay, so what we'll do is we'll take 15, we'll take a 10-minute break, and then afterwards I'm going to go over calculations for resistors in series and parallel. And then I'm going to go over a concept called time constant. So 10-minute break and then we'll start in. Yeah.
Yo, listen.
Oh, did you? Yes. Nick, this guy here is just, I'm going to go over series and parallel essence.
Okay.
Did you read the chapter?
I haven't had a chance to read it yet.
Well, and here in a nutshell, in a nutshell, when you have capacitors in series, the formula is the same as resistors in parallel.
Okay.
And capacitors in parallel, resistors in series. So when you have this, those capacitors are in parallel, then total is C1 plus C2 plus C3. And in series, it's CT is equal to 1 over CT is equal to 1 over C1 plus 1 over C2. I'm going to drive those formulas, but I mean, that's that. And then the other guy is multi-sim. Maybe you can arrange to come in and do that one.
All right.
So,
All right, thanks. Also, just a question of it, the idea or the concepts been rolling around in my head. Were we covering diodes at all?
no. Do you want to?
There was a specific, I mean, I'm sure like a lot of people come in here, musicians,
Yeah.
and there's a new type of overdrive pedal that they developed using this thing called molecular.
Molecular junction, okay?
Yeah, it's a type of diode replacing like germanium and silicon
Yeah.
diodes. And the concept of it it's over my head currently, but I would like to know more about it just for my own interest.
Well, I will tell you, that's the first time I heard of it.
Yeah, it's fairly new. It's developed by the by a group that does nanotechnology in I think Alberta.
Oh, molecular, okay, that makes sense. It's just a real small diode.
Yeah.
Let me look it up and I'll see if I can, do you know how diode works?
I know it's similar to like almost like a check valve that let current flow forward but not
Correct.
backwards.
Yeah. Let me see if I can, I teach this course on alternate semesters called Introduction to Engineering, and I go through diodes and how they work, the solid state diodes. And if I can get some lecture notes from that course, I'll print them out and I'll give it to you, you can read through it. And it's an introduction to engineering, so it's fairly basic.
Okay.
You should be able to understand it.
All right,
So,
cool.
and I'll see if I can look up that molecular diode.
Okay, cool, thanks.
Yeah.
When I saw a very basic diagram of it, basically saying it's like because seeing the capacitors reminded me of the way they explained it.
And you want to use it for what kind of application? Music?
Yeah,
For what, like a pedal?
yeah, for an overdrive pedal. I guess it's it provides a different type of clipping.
Oh,
I think a friend of mine, he's taken a couple electrical engineering courses, and he kind of looked at it as well, and
Yeah.
it had something to do with using a lower amount of energy to introduce clipping than,
Well,
traditional.
sounds
ways.
like that would work. There's a website that I use quite a bit called All About Circuits. It's free for anyone. And they have those kinds of high-tech, state-of-the-art articles. And they explain how that stuff is. So if you ever have any questions, that's a great website. And it's relatively straightforward, very easy to understand.